Hey, welcome back. So we've spent a lot of time so far talking about how Bitcoin uses cryptography to prove the integrity of the ledger. We've talked about the blockchain, we talked about fingerprinting, SHA-256, all of that stuff basically has been around this first point here, proving the integrity of the ledger. But Bitcoin also uses cryptography for a second purpose, which we've alluded to earlier by graying it out on this slide. Now we finally have a slide that emphasizes it.
The other half.
Okay, so we're going to talk about how Bitcoin uses cryptography to prove ownership of transactions. Basically, to prove that the Bitcoin in an address is mine.
Yeah.
Or that Kevin's sending me Bitcoin to prove that it's actually his to send.
Yeah. So when I send you Bitcoin, how can we be confident, A, that it was mine, and B, that you're definitely going to get it, and that I can't take it back?
Yes. So that's what the next, it's going to be a large chunk of videos, just not as large as what we just covered about fingerprinting and SHA-256 and the blockchain and all of that, but it's still going to be a pretty substantial couple of videos because there's a lot to talk about. We can't just dive into how it works without actually explaining some of the math and cryptography behind it, just like we did with we talked about fingerprint functions first, and then we applied it to the blockchain. We're going to do the same thing here. We're going to talk about the specific type of cryptography that Bitcoin uses, and then apply that to Bitcoin.
And don't be intimidated here. This will be a chunk of videos with some math, but this is a component of Bitcoin that extends much beyond blockchain. Public key cryptography, what we're going to go and do here, has applications all throughout computation and really is an amazing piece of technology that not a lot of people know about. And we're going to do our best here to make it understandable to somebody who has no background in cryptography or math.
So you might have noticed the title of this slide, or the first slide, is Symmetric Key Cryptography. And this is actually not what we're focusing on for the section. This is one video on symmetric key cryptography because what we're going to be learning is called asymmetric key cryptography.
Also known as public key cryptography.
Yeah, so we're going to contrast it. We're going to start by talking about symmetric key cryptography just in this video for like 2 minutes so that when we talk about asymmetric key / public key cryptography from here on out, you'll have something to compare it to. You'll understand the difference between the two.
So symmetric key cryptography, also known as shared secret cryptography, is a type of encryption. And we have the definition here: process of converting information or data into a code, especially to prevent unauthorized access. So if I want to send Colt a secret, how can I encode? How can I scramble some information so only Colt can decode it?
And we've already seen these slides on the Caesar cipher, but this is the most basic type of, I think the most basic. Maybe there's something simpler.
I think this is close to the most basic way
for
to do this.
Symmetric key cryptography. So I can encrypt something to Kevin, and we'll talk about why it's symmetric in just a moment. But yeah. I send him a message, hello. Once again, if you missed that video, all that we do is we have a little table here. We find the H. Where's H?
It's a V.
Yeah, and we do the same thing.
Find
for an E,
it's a G.
Okay, and we get this Vigitix. And then I send that to Kevin. He then has the same cipher. He has this table to look up and decode the information using that same thing that I used to encode it. He used it to decode it, if that makes sense.
So we both have the same copy of the cipher. We've shared it.
Same thing here with goodbye. Same idea.
And that's the symmetry, is that both of us use the same secret to both encode and decode.
So I encrypt it to Kevin using that cipher, and it's not limited to just things like the Caesar cipher. There's all sorts of symmetric key algorithms. It's a whole type of cryptography where I send Kevin some sort of encrypted data, and there's some key that I used, there's some magic that I applied, and then Kevin can use that same thing to go the other direction, to reverse it and get the original message back using the little bit of magic that I used, if that makes sense. It's sort of like a reversible cryptography. So to wrap that up, with symmetric key cryptography, which is also called shared key or shared secret,
shared key,
both the sender and the receiver need the same cipher. It all hinges on that. Yeah. Kevin has to have, if we're talking about the Caesar cipher, he has to have that little table that says what I'm mapping the different letters to in order to understand my message. So that he can go, I can encode it one way, he can decode it the other way. Again, it's not just the Caesar cipher. There are much more complex algorithms that still are symmetric, meaning that the sender and receiver both have to have knowledge of that algorithm. All right, welcome back. So in the last video, we talked about symmetric key cryptography really as a counterpoint for what we're actually going to dive into in this section, which is asymmetric key cryptography, aka
public key cryptography.
Yes. So everything we saw in the last video, again, it's not actually what Bitcoin is built with. Symmetric key cryptography, it's built with, or one of the things it relies on is public key cryptography. That's what we're really focusing on. We just wanted to show you something to compare it to. So now we can contextualize it a bit more. So public key cryptography is something that it's pretty cool. Kevin has some very strong feelings about it.
The next few videos are so cool. We're going to do our best to explain a concept that is really interesting, even if you don't care about cryptography or math.
Okay, that's all opinion.
I'm hoping that we're going to do our best to explain this in a way that a layperson can understand this, and hopefully my goal here is that our students leave here with an understanding of what is possible with this new form of communication, secret communication.
It's something that's really powerful, and it's not just relevant to Bitcoin. It's relevant to computing in general today, whether it's
all over the place.
It's all over the place, and there is some math involved, but you honestly don't have to understand every little bit of the math to understand the power and the utility of public key cryptography. So why don't we just dive right in? What is it?
So public key cryptography is a cryptographic system in the same way that a Caesar cipher or a symmetric key cryptography is a cryptographic system that uses instead a pair of keys, not just one. And one of those keys is public and one is private. And those two keys are produced by solving a very difficult math problem. We're going to go into a little bit of that, but in general, what you need to know is instead of one key to communicate, where both parties have the same key, in this case, there are two separate ones. There's a public key that anybody can know, and then there's a private key that only the creator of the key pair will know.
Yeah, and both of them are just really long numbers. And actually, this should sound familiar at this point if you've followed the whole course. We've talked about this idea of something that's public that can be shared with people, an address, for example, and something that's private that you keep yourself in order to get access to Bitcoin. So we've been using these terms, but now we're going to actually show the relationship between the two keys and talk about how they're generated and talk about the math. So stepping back, this is not public key cryptography, what we're showing you here. This is a diagram of a shared key cryptographic system like the Caesar cipher. So if you're colorblind, these are two of the same colors, green here. So you have a message, I encrypt it with whatever, let's say a Caesar cipher, send it to Kevin. He has the same cipher. He knows exactly how to decode it. He uses that same key. In this case, it could be a table that says A turns into X and B turns into Y or whatever it is. But he has a way of decoding it or decrypting it. That's shared key cryptography.
So we share the key in advance before communicating,
yes.
which is a flaw in that system. It's very difficult to securely share a key, especially if we're geographically separated.
Right. All right, so this is what public key cryptography looks like. So there are two keys. Basically, before anything happens, I could go on my computer and basically run this very hard math problem and generate a pair of keys, a key pair, public and private. And then I can share that public key with Kevin, for example, or with anybody and say, hey, Kevin, here's my public key. Next time you want to send me a message, whatever your secret message is, use this public key to encrypt that message. Now, what the encryption looks like, we'll talk about later, but just imagine that it somehow scrambles it up, whatever his message is, hello world, or how about actually it's coordinates to where he buried a body.
Yeah.
So it's some secret thing. He doesn't want anyone to intercept. He uses the public key I gave to anybody. He uses it, he encrypts it, we end up with a scrambled version. Then to decrypt it, I'm the only person who has the private key, unless I was a moron and gave it to somebody else, but I kept it to myself, and I can unscramble using the private key. So it's this different relationship. There's not one key that we're sharing. There is one thing I'm sharing with Kevin, but then I'm keeping one part for myself. Or I could share that public key with everybody in the world and say, anytime you want to send me a secret message only I can understand, use this public key to encrypt your message, and then I'll use my private key.
Yeah, so everybody can use the same public key. We can always use Colt's public key if we want to encrypt something that is destined for Colt. However, only Colt will be able to open it, because Colt is the creator of the key pair, and Colt has kept his private key, basically the unlocking mechanism, private.
So what's this have to do with Bitcoin?
Now we return to our analogy
of a Dropbox.
So these Dropboxes, Here we have a picture of a Bitcoin. There's just a letter B. This is the symbol for Bitcoin going into an open envelope. And this operation here that we described earlier on in our first and second iterations of explaining this somewhat crummy analogy of I can put Bitcoin into a Dropbox that Colt created, and then only Colt can open it. That operation is performed using public key cryptography. I actually use Colt's public key as the destination, as my Dropbox. So I wrap my Bitcoin with Colt's public key. And once that Bitcoin is locked onto the blockchain, then Colt will be the only one who can open it. Colt will be able to use his private key in the future to unlock the transaction that I stored on the blockchain for him. So this is a secure way for me to transfer something to Colt, and also consider the fact that once I put my Bitcoin into it, I can't get it back out. I don't have the private key corresponding to Colt's public key. I can't undo my transaction. And this makes the act of a Bitcoin transaction, once it's on the blockchain, irreversible. So Satoshi Nakamoto, whoever they were, took this concept of public key cryptography and applied it to transferring something of value on a network, on a distributed network. And this allows people on the Bitcoin network to transfer a piece of data, a Bitcoin, or some denomination of Bitcoin, to somebody else and make that transaction irreversible. And then once that person has that transaction in their possession or on the blockchain, nobody else can take it from them. So this is how we establish ownership.
So this is what really we're setting up the rest of this section to talk about. These diagrams are on the very, very simple overarching view of how this works, but we're going to dive into actually looking at some numbers, talking about how the public and private keys are generated, how they relate to one another, how the encryption and decryption works, at least at a surface level, but definitely deeper than what we're talking about here. That's going to be the bulk of this section, and it's going to take a couple videos to really see the big picture, so hang in there. All right, welcome back. This is going to be a really short little demonstration, but I think it's going to be nice. I'm excited about it. I think it will help explain how this stuff works. So we found this website, maybe not the most beautiful website.
It's beautiful. I like it.
It's beautiful in its own way, but it's really a nice simplified demonstration of public key cryptography. So what I can do is click this button, generate keys, and it will perform the difficult math problem we kind of have alluded to. However, it's going to give us two very short keys. The ones we're working with will be way, way, way longer and more secure. But basically, all you need to care about, it gives us a pair, a public key and a private key, and there's a very special relationship between the two. They're not just two random numbers. They are the outcomes of a difficult math problem.
So I'm going to walk away from the screens.
Okay.
And Colt is going to generate a key pair, and he's going to tell me his public key, and then we're going to encrypt a message. And we're going to see if Colt can then decrypt it with his private key.
Okay.
And hint, hint, he'll be able to.
Yeah. Okay,
so I'm stepping away.
Kevin. I'm actually going to hide the private key from you two for now, from everybody. I'm going to block it out on the screen in post-production, if I remember to do that. Okay, so here we go. Everyone can see the public key. Kevin, are you listening?
Yeah.
The public key is 251.
251.
Okay, so I tell him that. Now I'm going to refresh the page. And now we're starting from a blank slate. Imagine that now Kevin is at his computer, or he could do this on paper if he really wanted to. It'd just be some hard math. But he's going to send me a message about what are we doing? Where the treasure's buried?
My favorite color.
Wow, what a message.
It's a secret.
So what is it?
It's not going to be secret for long. Now, hold on. You're going to have to step away. Get away. All right, so now I'm sitting at Colt's computer through a different mic. And I'm going to type my secret message. Actually, are we going to block this out, Colt? I think we're going to block out my message too. Yeah. Okay, so we're going to block this out. And I'm going to type in my secret message. What is my favorite color? And my encryption key was 251. Yep. Colt, that was your public key? Yeah, 251. And now I'm going to hit encode. Okay, so we get this result. Stay back, Colt. We get this encrypted message. Hide this, and I'm copying and pasting the encrypted message. So here we have it. So I'm going to give this message to Colt, and he will hopefully be able to decrypt it using his decryption key. So Colt, come back. It's in your clipboard. So pretend this is happening across a geographic distance, not just across a room where Colt is standing facing the wall. And suppose that somebody is trying to intercept our communication. We're trying to communicate secretly. So the only information we've transmitted between us up until now is Colt has told me his public key. And now I've taken my message and I've encoded it, and I've written it on a piece of paper and sent it in the mail.
Yep, and I just got it. So here it is.
There it is. Colt has transcribed that.
So
and now
this makes no sense to anybody unless they have the private key to decrypt it. Now, I didn't tell this to anybody. I hid it from you actually as well. And I could still hide it from you. I'm going to do that right now. I'm going to hide this just for a second. I'm going to type the decryption key in here, which is my private key.
I'm not looking.
And I'm going to click decode. So here we go. The decrypted message is chartreuse.
Voila.
That's your, yeah, that's Kevin's favorite color. And voila is his favorite phrase.
Yeah.
So again, imagine, so I actually haven't shown you the private key at this point, so I could use it again. I could give anybody who wanted to send me a message, any of the allies on my team during this, or on my, whatever, my side during this conflict, send me a message encrypted with the public key 251.
Yeah. Now, if someone intercepted that, let's say the bad guy, let's say Hans Gruber, intercepts the piece of mail and knows that Colt's public key is 251 and then sees my scrambled message, there's nothing he can do with it.
Nope.
As opposed to if it were a Caesar cipher, then if Hans Gruber had the Caesar cipher and the encrypted message, he could just easily decrypt it. And this is really the innovation with public key cryptography.
Oh, by the way, if you care, my key was 5. That was my private key. So very easy to guess. In this case, like these tiny little keys, someone could just sit here and type, okay, how about 6? Is it 7? Is it 8? But the actual keys we're going to be working with are massive. They actually look something more like this. So here's a key pair. We can generate a new key pair. This is just a little online tool that we found that helps do this very quickly. So we've got private key, and this is in base 10. So it's a smaller number. And then our public key is this really long string. This is in hexadecimal. So the actual number in base 10 would be much longer. Okay. So it doesn't really matter what the numbers are, but just keep in mind when we say public and private key, we're not talking about 251 and 5. In the real world, we're talking about things like this.
Which are unguessable. You could
Yes.
have every computer in the world running for 1,000,000 years and you wouldn't guess one of these.
All right. Welcome back. So just like we did with hashing functions, where we explained the idea of a hash function, and then we actually went into the detail of explaining MD5 or introducing the actual implementations, MD5, SHA-2, SHA-3. Then we walked through and did some examples with SHA-2 and explained how it works. We're going to do the same thing now with public key cryptography. So we've talked about at a high level, you got a public key, you got a private key, and we've talked about how it works. You share the public key with anyone, you keep the private key safe, and you can communicate, or at least in one direction. Kevin can send me messages if I have the private key and he has my public key. And if I want to go the other way, I'd have to generate a new key pair, or he would generate it and give me the public key. But we haven't actually talked about any implementations. We've talked about it in general terms. Now we're going to introduce 2 specific implementations, 2 actual public key cryptographic systems.
So these are 2 public key cryptographic algorithms. On the left is RSA, and that's what we're going to cover in this chapter, in this video. And it's a lot easier to understand, but it accomplishes the same thing as Bitcoin's actual algorithm, which is ECDSA. That's a lot more advanced, but it has smaller keys. So the actual pair of keys, those numbers are smaller, but more secure. We're going with RSA because it's a little bit easier to understand. The math is sort of, you can fit it onto a single slide, and most people will be able to understand the basics of that math. Whereas ECDSA, which stands for Elliptic Curve Digital Signature Algorithm, involves understanding a lot more complex geometry to figure out the relationship between a public and a private key.
Yep. So we're just going to explain basically the same concept. It holds true between both algorithms, both implementations. It's just that the math itself is different. But the relationship between the public and private keys are the same. It works in the same way. These are just 2 different ways of doing it. RSA came along first, as Kevin mentioned, in the 70s. It was, what's it stand for again?
It's named after its inventors, Revest, Shamir, and Adelman, and that's 3, I believe, professors at MIT.
Yep. So in the 70s, I think you'll come to appreciate how crazy it is that they came up with this.
That they discovered this relationship.
I mean, it may be, I don't know, maybe people who are, cryptography majors and have PhDs are laughing at this, saying that, oh, it's actually common sense. But it just seems insane to the layman that we are over here coming up with this. And we're going to dive into the math now, but we just want to explain ECDSA is the real thing. So we don't want you to think that RSA is what Bitcoin uses. But the truth is, it doesn't matter as far as explanation-wise. It's going to be the same concepts. You need to understand the public and private keys either way. The actual implementation is hidden away from you in the bowels of Bitcoin. So before we actually talk about RSA, we need to just cover two concepts in math. If you're familiar with them, you can just skip through this. It's just going to be a minute. Exponents and modulo, two operations. So the first one, exponents, you probably are familiar with, or you may be. Modulo is a little less commonly used in the real world outside of programming. But exponents, let's start there. How's it work, Kevin? In like 2 seconds, don't bore us.
Exponent means multiply a number by itself that many times. So if you want 2 to the third power, so when you say exponent, you say to the power of this number. 2 to the third means 2 times 2 times 2, 3 times.
So we get 8.
8. So 5 to the fourth power means 5 multiplied by itself 4 times. 5 times 5 times 5 times 5, which is 625.
Okay.
So 2 to the fourth power would be 2 times 2 times 2 times 2, which is 4 times 4, which is 16.
Okay, so next we've got modulus or modulo. I don't know which. I think they're used interchangeably.
Both work, yeah.
We looked it up a while back on Wikipedia. They're both listed there. I kind of use them interchangeably too, I think. So the way that it works, it's also called the remainder operator. So I don't know how schools around the world teach division, but the way I learned division, before we talked about fractions or decimals or anything, we just talked about using the remainder. So we would say, let's say 9 divided by 2. You would figure out how many times does 2 go into 9 as a whole number. Well, it goes in 4 times.
4 full times.
So that gives us 8, right? 2 times 4.
But then
there's a remainder of 1. So I would actually I would do this little division house, is what we called it. 2 goes into 9, and we'd write 4 on top, R1.
Remainder 1. Modulus is just asking for the remainder.
Yeah.
So when we say 7 modulus 3, we're basically saying 7, when you divide it by 3, what's the remainder? So 7 modulus 3 would be, you take 7 divided by 3, and we get 2. And we know that the remainder on top of that is 1. So 7 modulus 3, or 7 mod 3, is 1.
Or here's another example. 11 mod 4. You figure out how many times does 4 go into 11 without a fraction. Just the largest whole number we can multiply 4 by that is less than 11. So that's going to be 4 times 2, right? So that gives us 8. So then we have 8 compared to 11. That means a remainder of 3.
So 11 mod 4 is 3.
All right, one more little quiz.
Mod 5. So how many times does 5 go into 12? It goes in 2 times with a remainder of 2.
Yep, 5 times 2 is 10. That gives us 12 minus 10, which is 2. So that's the end of the math review. Coming back to RSA, which again is just one implementation, the first implementation of this public key cryptography system.
Yeah, in the same way that MD5 and SHA-2 are just implementations of fingerprints.
So what we have to talk about here is that we've been saying there's a public key and a private key that are generated, 2 numbers. There's actually a third number that goes along with them.
A special number called M.
Okay.
So when you solve the RSA seed equation to generate a pair of keys, you get out a public key and a private key and this special number M. And M is going to, whenever you're transmitting this information to anybody, if you want to tell them your public key, you also have to tell them M because it's part of the calculation, how you encrypt it. For analogy's sake, it's just easier to think of it as one part is public and one part is private, and there's also a little thing that you always include with it.
So now we've established there's these 3 variables, these 3 pieces, and let's just say that the private in orange that just always stays private, and that's the one thing you want to bury wherever the safest place is. You don't want anyone to get that.
Yeah.
The public key in M, that's okay for
once
people
you generate those, you can just smack them on a billboard. You can put them on your website. You can put them on your business card.
You can we could have like a little circle around this, just calling this the public key.
Yeah.
But technically, for our math equation, you'll see why we're not doing that. So on the next slide, we have some math. Here we go.
Well, this is all the math. This is the RSA algorithm. Well, this is actually the RSA encrypt and decrypt step. We're not going to go into how you generate the key pair. That's a little more complex. But when you want to encrypt a message with the RSA algorithm, all you do, and remember, we think of a message as just a piece of data, and on a computer, you think of data as a number. So the word hello can be thought of as a number. A picture can be thought of as a very, very large number, but you can take that message and raise it to the public key. So the public key is also a number. So to encrypt something, you raise it to the public key, and you take the answer modulus m, and that output, that number right there, is your encrypted message.
Right.
Now when Colt, if I'm sending a message to Colt using his key pair, Colt has his private key. When Colt receives my encrypted message, pictured here on the bottom, Colt takes my encrypted message, which is just a number, and then raises it to his private key, modulus m, and the output will actually be the message itself, right, the original number.
So we're showing the math here, but in reality, nobody actually goes and does this math themselves. One, because you don't need to, there's code to do it. But two, the numbers are so massive that you can't just pull up like a calculator out of your desk and even type in a public key, for example.
No.
They're just way too long.
Yeah.
But it still works. The math is the same, and we're going to work with really simple numbers to start to just demonstrate that to you. But we're not showing this to you because you need to get ready to do this math yourself. We're showing it to you so you understand how these work together and the relationship.
And in terms of scale, these numbers that we're dealing with here are so much bigger than a fingerprint. A fingerprint is typically 256 bits. The numbers we're dealing with here are 1024 or 2048 or sometimes 4096 bits, zeros and ones. And those numbers are so unimaginably large that you would never be able to plug them into the biggest you'd need a calculator the size of a building to type them in.
Okay.
But what's neat is because we're using the modulus operator, there are some math tricks that actually make it tenable to do the exponent operation on them on a computer.
You're getting carried away, Kevin. It's good information. But here's just a review. So public key, I give Kevin the public key. He has a message he wants to send to me. He encrypts it, which again means raising the message to the public key, modulo m, taking the remainder with m, which was generated at the same time. He sends me that result. And then I take that result. I have my private key. I raise that encrypted message up to the private key, which is just a number. I mod the same m that Kevin used, and I get the message back out, which it's pretty crazy. So again, this does not work with just arbitrary pairs of numbers. It's very, very difficult to figure out a pair of numbers that this works with, or a triad, a
triplet.
Triplet, there we go. To figure out three numbers that, including m, that make this work. You can't just pick random numbers. This is not like a mathematical property of the world. This is a property of very, very special sets of numbers.
So here we have an actual triplet.
A really simple one. The shortest, I think this is the smallest one, right?
No, you can do smaller. I think like 1, 1, and 0 technically works. This is one of the smallest usable ones. So if you actually wanted to communicate with somebody but wanted to be able to do the math, you couldn't even do this math by hand. If you wanted to be able to do it with a computer calculator and no code that optimized it, this one would work.
Except it would also be pretty easy to guess, right? Because we know that we're working with small numbers.
Yeah.
But so this is not secure, but it follows the relationship.
Exactly. So our public key in this scheme is 7. Our private key is 23. And m, that extra number, is 55. So if Colt were to have generated this and wanted me to send him a secret message, he would just give me 7 and 55, and he would hide 23.
So suppose Kevin and we're, I don't know, in a foreign country, and we're
behind enemy lines.
And we're trying to rendezvous at some point in the next day. But we need to figure out a meeting time.
To bury that body.
Yeah, we need to figure out a meeting time. And Kevin's not just going to send it to me as plain text. And he doesn't want to use some sort of Caesar cipher because he would have to send that to me as well. And then if it was intercepted, then the whole jig is up. So we already have this public and private key pair generated. I have the private key. He has the public key in M. So I give it to him. And he's going to tell me the meeting time is 16 o'clock military time.
16 o'clock.
Or just anywhere that's not the U.S. time.
Yeah, the rest of the world. So to give Colt this secret message, 16, without having actually shared anything other than the public key. What I do is I take 16 and raise it to the 7th power, modulus 55.
So 7 is a public key.
So 16 to the 7th, mod 55 is 36.
And let's just take a moment. 16 to the 7th is a big number.
Yeah, it's pretty big.
Even though we're talking about small exponents here, 16 to the 7th grows really fast. This is 16 to the 7th right here. So those are two small numbers. This is a 2-digit number raised to a 1-digit number. Now imagine we're talking about numbers that are huge, like way, way huger. Now imagine potentially a number that's more than 1,000 digits long. These numbers more than 1,000 digits long. The result is just going to be massive.
So back to our mini example. I've encrypted this message with Colt's public key, our 4 o'clock rendezvous time, and it comes out to be 36. I can just broadcast this over a completely insecure channel.
Yeah, he just goes out and starts yelling 36.
I can just
like
shout 36, and I think people would realize that we're up to something no good if I'm shouting some people would think something was up if I was just running down the street shouting 36.
Anyway, he says 36, or he gets that to me somehow. If you're shouting the data 36 across the street, and somebody knows the public key
and the modulus
and M, can't they just work backwards?
So unlike a plus, or unlike an exponent, or unlike a multiplication, you can't work backwards in a modulus. It's a one-way function. So the one-wayness of modulus means that when you actually perform modulus on that really big number, 16 to the 7th power, which was what, about 2 million or something, 20 million?
Yeah, it was a long number.
It was a big number. When we modulus 55, we really lose a lot of information there. We get 36. There's a lot of division pairs that when you take this number, mod 55, the output is 36. You can't work backwards with just 36 and a modulus 55 to determine what the input was. You might be able to narrow it down given the fact that our public key is just 7, but at the scales that real RSA keys work at, there's absolutely no way to reverse the modulus operation. Yeah. It's a lossy one-way function.
Yeah, and that's different than multiplication and division, or addition and subtraction, or exponentiation. It's kind of unique in that sense as far as the traditional day-to-day math that people do.
Yeah.
So then on my end of things, I have the private key.
So Colt hears someone shouting 36 walking down the street, and he's like, oh, that's probably Kevin.
Yes, and I know my private key, and I know M, which again was public. So really, it's just the 23 that I need to keep secret. So then I take 36, his message, I raise it to the 23rd power, which is going to be a really big number again. And then I'm going to mod by 55, which trims that all the way back down to 16.
And let's look at 36 to the 23rd, mod 55, just to prove that that's true. So now we're at Wolfram Alpha, which is a much more powerful online calculator than just Google. And why are we here? Because 36 to the 23rd power is a massive number. So we take 36 to the 23rd power, mod...
Well, let's just look at that number first.
Oh, there's the exact number.
So
that's a good calculator.
That's the number itself.
So let's do that guy, mod 55. Copy and paste
scientific notation really is not cutting down on this. Okay.
So we grab the number.
I'm going to paste it in here.
And then we do space mod 55. Is 16, and that's the original input.
Yes. So you can see the math is really complicated. I mean, it's feasible that we could do it by hand, even with these small numbers, but to multiply something out to this, you got to be pretty good at multiplication by hand and not make any mistakes and have a really long piece of paper and a lot of patience. So that's the relationship. Again, Kevin takes a message, in this case, just the number 16, raises it to the public key, mod 55. Then I get that encrypted message. I raise it to the private key, mod the same 55, and I get the original message back. It's pretty cool. And this only works with special key pairs that are the result of this crazy math problem that generates M and the public key and the private key. So we're going to end the video here. I know it's a lot. Just keep in mind that you don't have to be able to do this math. The computer takes care of it for you. Bitcoin does all of it for you. It's just cool to understand how this works. And it's pretty magical. Okay, we're just going to end the video now.
Voila.